Maybe let's start, if you're okay, Emil.
Yeah, all good, man.
Hi, everybody. Welcome again to another session of the Neuro-Symbolic Alan Turing Interest Group. We're happy to have Emil giving us a talk today. Some of you might know Emil if you attended the recent Neuro-Symbolic AI conference in Barcelona. So Emil finished his PhD in 2024, right, Emil, in the Vrije University, and he's now a postdoc with us at the University of Edinburgh with the NLP and the group as working also with Antonio. And he's done a number of different papers on fuzzy logic, understanding operators in terms of their differentiability, as well as their expressiveness. And he continues to build new tools for loss functions in Neuro-Symbolic AI. So we're very happy to have Emil here. Take it away, Emil.
Thank you, Faisal, for the very nice introduction. Indeed, I'll be talking about logic, about differentiating through logic in particular. Wait, that doesn't work. So let's consider this self-driving car scenario. Maybe you even saw it in the last talk when Eleonora gave it. So this is a scenario when a car is driving through the world and it tries to observe things in the world and say, well, that's a traffic light, that's a pedestrian, etc., etc. And now it sees a traffic light that's red and green at the same time. Now we know from our knowledge of the system of what a traffic light is supposed to do that it cannot be red and green at the same time. So we found a legal prediction, and our logical background knowledge of the world should say to us that this shouldn't be allowed and that we should correct our neural network that is making these predictions in some way. And a big part of this talk will be about how do you do that. So here, the main philosophy of using logic to correct a neural network comes from this main idea that I have about Neuro-Symbolic, at least the way that I have been working on it, where you try to find a neural network that exploits the data that you have, but also the knowledge that you have about the problem in the best way possible. So that's kind of like, compared to regular machine learning, we only have data and we ignore the knowledge. But here we try to find a neural network that performs best given both data and knowledge. Jan LeCun also thinks that using reasoning and planning, which is in a way exploiting knowledge or reusing your logical symbols, can be useful, especially when it's based on gradient-based optimization, which is what I've been studying, to give these ideas, this knowledge, to the neural network. However, he's a bit skeptical about how to do it. He says that you cannot make logical reasoning compatible with gradient-based learning because it's discrete and non-differentiable. I beg to differ. We can actually differentiate through logical reasoning, and it's pretty well defined. So I have been studying essentially the plug that makes neural network computation, which is very continuous and smooth, and symbolic computation, which is discrete. I've been studying the plug to make these two work together in a single coherent framework. And differentiable logics is the kind of term I use to describe how to best integrate these two. Roughly, the idea is that given a neural network, you give it an image, and a neural network is going to give predictions about the symbols on the image. And then we're going to use differentiable logic, taking in the knowledge that we have to constrain the output of this neural network. And that way, we get hopefully some guarantees about what the neural network is going to do. This will allow us, by using logic to interpret the symbols on the image via this neural network, to add some proper reasoning so it can generalize compositionally. We can ensure some requirements to be verifiably safe and robust, which is very important in many different application areas. We can improve data efficiency. The way I like to see it is that knowledge contains infinite data because it can always be reapplied on any kind of input. And finally, it will help us explain decisions if we use these logical layers to make the final decision instead of the neural network itself. So there is roughly two ways in the current literature to make logic differentiable. The first is using fuzzy logic, as Vaisak already mentioned, where you study the fuzzy truth value of a formula. The second is using probabilistic logics, where you study the probability that a formula is true. Both are differentiable. It sounds like, so is that all? We just use these instead of your regular logic and you're done. Yeah, I would say there's a lot more to say about this topic. So let's dig into what kind of things we can say about both of these logics, but also about how to integrate this with neural systems. So let's start with fuzzy logic. And indeed, I studied these different operators that you can use in fuzzy logic. So roughly the idea here is that you relax logical semantics, where instead of having a Boolean logic, where things are either true or false, you now have truth values between 0 and 1, in a continuous, taking continuous values between 0 and 1. And your operators like and or and implies, these are now differentiable operators on these continuous truth values. This is a pretty easy way to convert your knowledge into something differentiable. You just evaluate the formula as given, changing the ends into these differentiable operators, etc. So like one way to see this is, you have your neural network, you predict the symbols. For example, you predict the probability that red is true, the probability that green is true. So the probability that the traffic light is red, probability that it is green. You encode your knowledge, which here is given as phi, as not red or not green. One of these two needs to be true because they cannot be on at the same time. So one of red and green needs to be false. And then you apply these transformation rules for fuzzy logic to get a differentiable function, which is down here, taking the maximum of doesn't the softmax really do this? So the softmax does do this, of course, but that depends on how you model it. So if you don't assume, if you assume that these two are different options in your softmax, then you already guarantee it. Indeed, there is no problem here. But that depends on how you model your problem. If you see these as separate sigmoid output layers, then you have to do this. In practice, you can enforce it with a softmax in this case, yeah. But this is a very simple example to express it. I cannot see my mouse, which is really annoying, so I don't know how to close the chat. Oh, there we go. Okay. So there is multiple ways to translate these logical operators. So we can use a Gödel, the product t-norm, the Lukasiewicz t-norm. Don't worry about these formulas here, but there is actually an infinite amount of ways to interpret these and these ors, for example, and basically rewrite your formula with this fuzzy logic. So the question might be, well, okay, if there is so many of them, how do you choose which one is the best, which one you should use in different situations? And we have a long journal article essentially going through many of these cases and saying, okay, well, these things, this particular set of operators have these benefits, while these have these downsides, etc. So let's give you some examples of the weird things that might happen. So for example, with the pretty common product t-norm, here you basically see an and as a product of two symbols, but here you get already into some very interesting and possibly surprising behavior. Now, if you evaluate this formula for something like the probability, or like the fuzzy truth value of A, you just compute the truth value of A. But if you now compute the truth value of A and A, which is obviously logically equivalent to just seeing A, you would compute the truth value of A times the truth value of A, essentially decreasing the truth value. So a very classical equivalence in logic, A is equivalent to A and A, does not hold if you use a product t-norm. What this basically means is that the way that you write down your knowledge in with these product t-norms can actually change how your loss will behave, giving you very different loss landscapes or encoding different kinds of beliefs. And this can make it pretty hard to get these things to work, because actually different ways you write your knowledge will make you perform better than others, which is not something that you would expect when you write down a logical formula. Another example is with this Lukasiewicz disjunction, which is also used quite a lot. This thing is a bit more complicated. Essentially, it sums all your truth values together, and then it cuts it off at 1, if it is higher than 1, the sum. So if you have a very big disjunction of things, right, you can make this thing true by making sure that all your different truth values that you have in this thing that you're summing over, that they all sum up to be above 1. But if you have 1,000 things to sum over, it's actually pretty easy to be above 1. You know, on average, the things that you sum over needs to be larger than 1 over 1,000, which is easy to satisfy. But if you set all these fuzzy truth values to 1 over 1,000, you're, in my opinion, saying, I don't think any of these are particularly true. Yet, we can completely satisfy this formula by basically being completely unsure over all the different elements that you sum over. Another problem with this is that usually you won't have any gradients when you're doing this, because every time that you're above 1 when you sum all these fuzzy truth values, you're going to have no gradients, because this Lukasiewicz disjunction cuts off your, it basically clips it at 1, and meaning no gradients are allowed through. What that means is that for many examples that you give this Lukasiewicz disjunction, it's just going to cut it off, not do anything, meaning no learning is happening, which can make learning quite inefficient. And we see this happening in many experimental results too. Especially interesting is studying implications. So in this application where ravens are black, we now have a robot that says it sees a white raven, which goes against our background knowledge, right? Because, well, we now have the background knowledge that ravens are black. So there's also a whole load of literature about how to translate these implications. So one way is this Gödel implication, which basically looks if the antecedent, which is raven, if that is smaller than black, the consequent. If in that case we just say, you know, it is fine, we've satisfied our implication. That's basically this upper triangle you see on this plot. Otherwise, we are going to return the value of the consequent, in this case black. So in this example where we have our robots predict that it sees a raven with truth value 0.9, and it sees black with truth value 0.3, well here the antecedent is higher than the consequent, so we are going to return the value of the consequent, 0.3. And then differentiating that, we see, okay, we're going to increase the value of black in that case, which makes sense. You know, raven is true, we should probably also make black true. But even when raven is only slightly more true than black, we are still going to give it a positive gradient signal, because it only looks at whether the value of raven is larger than black. So in this case, when the robot says 0.2 and black 0.1, it is still going to suggest to the robot that it should increase the value of black. And it turns out that this is a pretty bad idea, also experimentally, as we have shown. So at the end of this, we kind of concluded that, you know, fuzz logic, it's an easy way to make logic differentiable, but the semantics that you're actually using can be quite brittle. In fact, the things that work best in fuzz logic will come by essentially hyperparameter tuning. You just combine different fuzz logic operators together, different ways of writing your knowledge, and then you just hope for the best. So theoretically, it's maybe arguably not the most principled way. Probabilistic logics is arguably a more principled way. Here, you study the probability that a symbol is true, in particular the probability that a formula is true. It gives very well-defined semantics, where we no longer have this issue where the way that you write down your knowledge matters for the kind of things that you're going to compute, kind of losses and predictions that you're going to make. The way that probabilistic logic works is quite different from fuzz logics, where you just evaluate the formula. In probabilistic logics, you apply something called weighted model counting, which you see in the bottom left here. Roughly, the idea is that you're going to use your neural network to assign some probabilistic preference to certain combinations of symbols. Then you have your logic to say which things are allowed. Essentially, it acts like a filter over the kinds of things that you can combine. So the weighted model count is essentially a very big sum over all the ways that you can assign your symbols, giving them all some kind of preference through your neural network, and then filtering out the combinations that are not allowed. So for our formula, which I forgot to add here, where you have not red or not green, there are 3 different combinations of these symbols to make it true, namely red and not green, not red and green, and not red and not green. And then we simply sum the probabilities of these combinations together. I will explain this a bit better with an example of A-NeSI addition. This is a very common task in the current Neuro-Symbolic literature. It's a bit toyish, but it allows you to really see when you implement something in Neuro-Symbolic, is the thing that I'm trying actually working. So here the idea is you get some A-NeSI images, and you know only of their sum, and you need to learn how to recognize A-NeSI digits from that. So we can again use this weighted model count to see how that works. So let's say that we know that the sum is 13. Then we're going to use our neural classifier to get probabilities over your digits and say, well, the probability that 5 is true, the probability that 8 is true for each individual digits. Then a constraint looks at the combination and sees, okay, is their sum together equal to 13? That means that we're going to sum over different options. For example, 4 plus 9 makes 13, 5 plus 8, 6 plus 7, 7 plus 6, 8 plus 5, and 9 plus 4. They all make 13. So we need to sum over all of these options and compute their probabilities. Then we can simply use maximum likelihood estimation to optimize this loss function. Now this is great, but there are some issues, because if you scale this to more options, where you have now sum of 3 digits plus another sum of 3 digits, there is way more options to consider. And if you do naive exact inference by just running that sum over and over, you would need to sum an exponential number of options. So can we do better there? We can, luckily. But this does require making some assumptions. So first of all, we have to make a conditional independence assumption. And this thing I will return to later in this talk. The assumption here is that if you're given some input, then the different symbols that you are predicting are independent. So in this case, if you know what the input x is, then the probability of red and green is equal to the probability of red times the probability of green, essentially saying the probability of red is independent of green given x. Then secondly, given this assumption, we can now compile into a tractable computation graph called a probabilistic circuit, and that can allow you to do exact inference over this sum and scaled pretty far. And in fact, today there is a new paper that allows you to do this for these kind of arithmetic options to scale very far. But what I'll present here has not taken this into account. And so this way of compiling into these tractable computation graphs is used in the prop logs, semantic laws, semantic probabilistic layers, etc. It's used very often. But back in the day when I made this paper, it was still really hard to get this eminence addition to work with exact inference. And in fact, the amount of time it takes to perform this problem scales exponentially with the number of digits that you want to apply this on. So if you go from 2 to 3 digits, the time it takes extra to compute these loss functions increases exponentially, meaning you cannot hope to scale to large amounts of digits. Now, that's a big issue for these probabilistic methods. So can we make it more scalable somehow? This is what we did in our paper A-NeSI, where the idea is to use a neural network which is going to learn how to approximate this very complicated sum, this weighted model count. So we're going to train this Q of phi to basically imitate what this weighted model count is going to do. The good thing is, as I said before, knowledge contains an infinite amount of data. So what we can do is we can make a simulated process that uses just your background knowledge and some prior over inputs. And then you're going to simulate from this knowledge many kinds of W's and Y's, which allows you to train this prediction model, this neural network, without any external data. It can be done just from the knowledge that you have, just from the logic that you have. So then you essentially have trained your neural network to imitate this weighted model count, and we can simply replace this neural network in our loss function to obtain a new one that's completely differentiable while being very scalable, because it just requires you to evaluate this neural network. And that turns out to really work. We were able to scale on this addition task to 15 digits with basically almost linear overhead by increasing the number of digits. And we also were able to scale to more complicated tasks like this shortest path finding problem, where you see a Warcraft model, a Warcraft map. It's like a 2D image of in a game. And the goal is to compute the shortest path from the top left corner to the bottom right corner. Now here, using this weighted model counting, which is a usually very expensive thing on a 30 by 30 grid, and previous methods were not able to scale to this. It's a slightly different setting, but you wouldn't be able to scale this to 30 by 30. But we were able to scale this in the following way. We basically predict on the grid what is the cost of traversing that, and then running Dijkstra's algorithm to find the shortest path on that grid. And this can be done with probabilistic reasoning to figure out how to learn how to find these shortest paths. And for this we did reasonably well. Some other methods, especially on the larger grids, still outperformed us, but yeah, there's more work to do there. Okay, so the scalability issues of probabilistic logics, they are definitely a thing, but my hypothesis is that approximate inference, very well designed approximate inference, can really help. And there's also still a lot of work done on scaling up this exact inference. That's not what I focused on, but I think for probabilistic logics, there's just a lot of work into making these things more scalable and more approachable. So are we done then? I wouldn't quite say so yet. So there was one big assumption that we talked about, and I will discuss this here. So this is slightly more, I don't know, philosophical, right? So what do we actually want to do with these losses? So say that we again look at this image and we know, okay, the probability of not red or not green should be 1. We want to make sure that our neural network will never violate this assumption. We can essentially do this by making sure that the probability of predicting red and green together is 0, because that's essentially what this constraint says, right? Now the question is, how do you correct that? How do you correct your neural network whenever it sees a traffic light that's red and green at the same time, if we know that it can never be red and green at the same time? Now it turns out that that's a pretty challenging question. So the reason for this is we don't know whether it was a red light, a green light, or if they were both off. We don't have this data. We only know that what it currently did, that it was red and green at the same time, that this is an invalid way of predicting. So our neurosymbolic system should somehow correct our neural network and say, actually what you should have done is, in my opinion, is that in this case you should say, well, I think it might have been red or it might have been green. We don't know because we don't have this information. So many of the current neurosymbolic systems use an independence assumption, as I said before. So given your input image, x, the probability of red and green is equal to the probability of red times the probability of green. Now, what does this assumption imply for our problem where you're trying to correct your neural network? For this, we're going to study a tetrahedron. I hope I cannot see myself, but my webcam it was going to work. So a tetrahedron is essentially this nice three-dimensional figure here. It's essentially a weird triangle kind of thing, right? And it basically tells you about the different beliefs you can have about the world. So at the top of this triangle, you have the case where you have a full belief in red and green. While at the bottom, you have the beliefs that are fine. For example, those are the beliefs where you have a full belief in red and green being true, a full belief in only the green light being on, or a full belief in the red light being on. But you can also be somewhere in the middle. So you can say, well, in the very middle of this triangle, it's a 3D thing, you kind of have an equal belief over all your options. Or if you are here in the middle of it, middle of this triangle, you can say you have an equal belief in the green light being on, the red light being on, and then both being off, etc. So you can kind of like mix probabilities in that way. Now, remember that we are using an independent distribution in current neurosymbolic models. That means that we have only two parameters to represent this. But we live in a 3D space, right? It's this tetrahedron thing, which is a 3D object. I can feel it here. So somehow we are representing a 3D space with two parameters, which is not enough to completely fill it. So is there a way to say, okay, well, if we are using only two parameters to represent this 3D space, can we say what it actually does in this case? And yes, we can. So under this independence assumption, the distributions that are allowed by our constraint are going to be this blue line. Now, the bottom of this triangle is essentially where we're going to say these are the distributions that satisfy our probability mass. These are the distributions that satisfy our constraint. And this is because they don't assign any probability mass to red and green being true. However, under this independence assumption, many of the points inside of this triangle cannot be modeled. In fact, there is kind of like a rule that explains what this independence assumption creates for you. It basically says at least one of the probabilities is 0. So either the probability of red or the probability of green needs to be 0. So we now have a way of studying where these distributions end up. But what does that mean? In my opinion, this is quite problematic. So, because there are many probability distributions that I think are very interesting to study. In particular, this point P2. This point P2 gives an equal probability to the green light being on and the red light being on. And that's exactly the point I talked about earlier. If we don't know whether the red light or the green light was on, but our neural network made the mistake that the red and green light was on, we want to end up in this point P2, where we are not sure which of the two cases should be true. But clearly, on this independence assumption, we are not able to get to that point because our model is too restricted to be able to get there. There are more issues with this independence assumption. For instance, the minima that you find, for example, exactly these blue lines, they are non-convex, which means in optimization terms that they are hard to optimize. Because you need to figure out really weird ways of going from one place to another. And there are other issues here, and this appears, for example, in A-NeSI addition that I explained earlier about adding numbers together, where the minima of the losses that you're going to use are disconnected, meaning you have to go through high regions of loss to go from one point to another. So all of these issues, the non-convexity of your loss landscape, inability to model uncertainty, and these disconnected minima, they all appear in a general way. This is not just for this particular formula where you have that a red and a green light, that you cannot have a red and green light at the same time. This actually happens for basically any kind of logical formula, logical knowledge that you write. And this really challenges the optimization when you're going to apply these semantic loss functions, these neurosymbolic loss functions. Luckily, there is a caveat here, but you can relax these independence assumptions to decrease the impact of these issues. So by adding dependency structure between your different variables, your different symbols, you can actually decrease how much these issues happen. That doesn't come from free, because it makes your the things you need to calculate way more expensive. But that's a discussion topic that we are currently very interested in. All right, so we have this fuzz logic which has these brittle semantics where it's a bit hard to figure out how to write your knowledge. And then there's these probabilistic logics where the semantics are much better defined, but they are a bit harder to scale. And then there's also general challenges in differentiable logics, like I just explained with this independence assumption, but also another challenge that is very central, reasoning shortcuts. And especially this one is kind of like the core central problem, combining all of these together. So here there's another traffic light scenario. It's slightly different. But here you have the formula that if you see either a pedestrian or a red light, your car should stop. Right? Very simple formula. If you see a pedestrian or you see a red light, you should stop driving. Or you should brake. Now a reasoning shortcut is essentially saying if you have a different way of interpreting your symbols than you would expect from your image, you can make this logical formula true, even though the semantics that we intend from interpreting your image is completely different. For example, if we see all pedestrians as red traffic lights, we would make sure that our car always brakes whenever it sees a pedestrian, right? Because it sees, okay, that's a red light. Okay, it's actually a pedestrian, but it doesn't know that, right? But it would behave according to the logical formula that we give it. This means that we might be able to solve our problem and get perfect accuracy on the training set, but then when we apply it to new scenarios where we need to use the fact that someone is a pedestrian and not a red traffic light, and our model would make very grave mistakes. So in other words, our neurosymbolic models can get very high accuracy while learning completely wrong concepts. So in our UAI paper, we've been studying how can we do better than this. So where current neurosymbolic models mostly make these mistakes when you get into these reasoning shortcuts, our method BEARS allows you to be uncertain about multiple options. So in this method, what we are essentially doing is we are saying we are going to train multiple methods and making sure that they all have different predictions. And this way, by having multiple hypotheses, we can try to see where things go wrong. So the high-level picture here is very similar to different neurosymbolic methods that I explained earlier. But instead of having a single neural network, we're going to use multiple neural networks. They're all going to do exactly the same thing, this neurosymbolic thing where you're going to optimize these loss functions. But by having multiple neural networks, all being very different, having different hypotheses of how the world looks like, we can figure out where we are uncertain. And if we know that we are uncertain about something, we can fix it. Because in cases where there is no way to disambiguate between, for example, the red traffic light and the pedestrian, our method BEARS would be able to detect this and say, wait, this pedestrian and this red traffic light, these are concepts that we cannot recognize correctly, and we will need external knowledge or external human annotators to improve our accuracy, so we can make our models better. And this way we can add, more safety in a human AI loop, where our method tells us where we might be making mistakes because of incorrect deductions of our data and knowledge. We've been studying reasoning shortcuts, especially with the people in Trento, for quite a bit. And now in NeurIPS we have a data set called RS Bench, Reasoning Shortcuts Bench, containing 8 neurosymbolic tasks with explicit reasoning shortcuts, so you cannot solve them correctly in a way, and you need to be able to disambiguate them. And these 8 tasks here you can use to study how robust your neurosymbolic method is to these reasoning shortcuts. So finally, I want to talk about accessibility. So you might be intimidated by this slide. I'm always intimidated when I look at this. This is all different ways of writing down this A-NeSI addition task that we discussed earlier. So as you can see in different papers like Deep Problem, NeurASP, Logic Tensor Networks, NeuroPSL, there's all these different kinds of ways of describing how to do this summation. And I would really need to look for a long time to see, okay, well, how is this working in this new language and how it's looking in that new language. But often when you make your new neurosymbolic method, you need to compare to all of these. and you need to write down your method, you need to write down your logical formula in all these different languages. But really what these languages do is often quite similar. For example, with the ProbLog and NeurASP, they both use probabilistic semantics, meaning that the loss function you get from applying these two programs is actually the same thing. And really, these two should not be doing anything different in terms of how you're going to train your neural network. So these are some issues that we've been facing for a while as researchers in Neuro-Symbolic. And we are now looking into how can we make this easier for newcomers. So how do we make writing down your knowledge for your experiments, but also for applications, easier? And for that we are developing Euler, a unified language for learning and reasoning, which is a Python library that is with the goal to make experimentation Neuro-Symbolic easier and also more accessible in particular. It's a Python library to provide a shared language to express your knowledge in, and we are going to wrap around existing Neuro-Symbolic inference engines to work with this knowledge and to compute loss functions and Neuro-Symbolic layers and things like that. For example, here is the way you would write down the eminence addition case in our language within a Python program essentially. So given two input images and a sum, you're going to run your these two images that you get through your model, and then you're simply adding them together and comparing whether they are the same as the sum that you're given by the data. So especially for people with a more machine learning background, which is kind of what we aim at here, there should be a fairly straightforward way of writing down your knowledge in a more procedural Python-like manner. So we are developing Euler to make Neuro-Symbolic research more accessible, reproducible, and we want especially to make benchmarking easier so people can write down their benchmarks and share them more easy with other people. We are soon going to release an open source library. If you want to stay updated, you can very quickly scan this QR code. I should have put it on the last slide, not on this one. Yeah, so we hope to release this soon. We already presented this a bit at the A-NeSI conference early September. All right, so that was all the challenges that I discussed. So the main challenges that I discussed were the brittle semantics of fuzz logic, where we saw that by analyzing their gradients, we can get some useful insight in what these things actually do in practice. My recommendation would still be to see if you can use probabilistic methods and see if you can scale these or get them to work. It's not always as easy, but I think in many applications where you really need to get down to the logic, it will give you much more stable reasoning. And the scalability of these probabilistic logics is still complicated. We gave a first shot with A-NeSI. This is a pretty active area right now with many approximate methods, but also many people working on scaling up probabilistic circuits and exact inference. Then we studied the independence assumption that is very often made in Neuro-Symbolic methods right now. And as I showed, you cannot represent uncertainty there. Now, one way to get around it is by using more powerful models, like, for example, the models in generative AI. Combining this with A-NeSI is highly non-trivial, but I think it's a super interesting challenge that already some people have started exploring. For example, in Guy van den Broek's lab, working on combining large language models with constraints, which can, with some approximations, actually work quite well. Then reasoning shortcuts, basically the fact that you can get perfect performance on your training set while never really figuring out the right concepts. We saw some way to get around this by quantifying uncertainty, so you know when when you are in these cases of these reasoning shortcuts. And finally, the accessibility of A-NeSI, which I think can really be helped by good engineering open source libraries, for example, with Euler. So, take home, logic can be differentiated. It's not that easy, but I think as a community we should be working on tackling its challenges. Thank you.
Thanks a lot, Emile. So people who want to ask questions, feel free to write it on the chat or speak away by unmuting yourself. While people are trying to do this, Emile, I had two questions myself. One question was regarding your reasoning shortcuts example, and I wondered how much of this is a result of an under-constrained specification. I mean, adding a constraint to say that pedestrian is not the same as red, which seems obvious, common sense knowledge. What would that do in terms of the training?
Yeah, that actually is not enough, because they are indeed not the same, but your neural network is going to predict something about the world. And you can say, well, pedestrian is not the same thing as red, but that doesn't say anything about which of the particular instances are pedestrians or red. So it can still say everything is a red light. That still complies with the logic that pedestrians are not the same thing as red.
Right. So it could just say there are no pedestrians at all in general. Yeah. If they were, they would be different from red. Right. Okay.
Yeah. That still complies with logic.
Good. Yeah. Makes sense. Good answer. The other question I had was, I mean, if I'm trying to look at what your first two parts of the talk really implied. On the one hand, you said it's the independence assumption that allows for scalability, and even that, it's not guaranteed. I mean, as you wrote for both fuzzy logics and probabilistic logics, they have their issues with scalability. Fuzzy logics may be a bit better, but nonetheless, they struggle too. Certainly with LTNs and so on, they struggle with, as you go up to larger constraints. So the question then is, where do we see this going? I mean, did you, in your work on the independence assumption, did you work out a way in which you could get, a differentiability with scalability despite not making the independence assumption? And if you didn't, what is there to say? I mean, is it the case that there is still a reason to continue working on differentiability as opposed to, let's say, a more modular approach, which is what people built, in the good old days where they had a neural network that would be interpreted as a concept in a completely logic solver, right? So the logical part would be separate from the machine learning aspect. The disadvantage, of course, is that the network could give you a lot of invalid samples.
Yeah.
I mean, but this is a well-known issue, but it seems that from a scalability point of view, we don't really have a silver bullet yet.
No.
And I'm not sure what would come up that could change that story.
Yeah, neither do I. So like, you can never, I don't think it's possible to do it with the most powerful model and the most general logic. And even with the most powerful models, you're never going to be able to really scale this to even the simplest constraints. So even if you have a large language model and you want to constrain it to never say a bad word or whatever, it's a really simple constraint. But you can never exactly do all these probabilistic reasoning things with these large language models. But I think there is now quite a bit of literature about how you can still sample from it, given these constraints, where you do some smart tricks with importance sampling or trying pseudo likelihoods, that's what pseudo semantic loss, and or even these RLHF things that currently are very common in natural language processing, where you're essentially learning or fine-tuning your language model with a new task, like a constraint or a reward, and then to figure out how to best adapt the parameters of your neural network, of your large language model, to comply with the constraints. So there are definitely quite a few options for getting this to work.
Okay. I'm not entirely convinced, but I take your word for it. There's a question, two questions. In fact, there's also a question in the chat, but I think this might refer to something really ages ago, to your first few slides. If you could read out the question and answer that, and then I think it's Erman first and Michael next.
Hi, Emile. Thanks for the talk. Well, every time I listen to Emile, I get new questions, even on the same things. So it's very nice. Yeah, so this is kind of a clarification question. About the independence assumption, right? So one of the main promise of the semantic laws and the related fuzzy logic one and the deep block one, right? So that's very good in, let's say, semi-supervised learning, right? When the data is unlabeled and all. So would it be correct to think that when we relax the independence assumption, right, on some problems, we a bit lose on that ability for the semi-supervised learning to some extent? What is the trade-off there?
Not necessarily, I think. I mean, you can define it exactly in the same way. You can still define semi-supervised losses on more powerful models as well. That being said, it probably will be a bit harder, again, because of the scalability issues also that Vaishak discussed. So how do you properly constrain these models? But also, yeah, you just need more parameters and more computation usually to have these more powerful models. So sampling from that or computing these circuits, it's just a lot harder. I think there's a lot of opportunity there, though. I don't think this is a case of, you know, we are okay. It's too hard. We can do it. I actually think I'm pretty positive that there is a lot that we can exploit there, and especially with the way that current neural network training is going. It's a lot more compositional, a lot more reusing existing knowledge. I think there is a lot to exploit there, where you can essentially say you can already condition your neural networks quite a bit in a very, very nice way with you know, prompts, but also with these RLHF, and in diffusion you have control generation. You already have a lot of tricks to kind of control your neural network. It's not as perfect as the kind of guarantees we get in Neuro-Symbolic AI. But I think if we look a bit into what the people in deep learning and people in generative AI have been developing for controlling their models and combining these ideas with the more strict requirements we have often in Neuro-Symbolic, I think we can actually get quite far.
And maybe very quick follow. So, but if we know that they are independent, right, by the world, so this is still our kind of best shot, right? Just
yeah, if they are independent, then it's like you don't really need to add this to your model. In practice, like there is not so many things, many data where this independence really holds, right? So, yeah.
All right.
If they really are purely independent, which I think is very, very rare, then yes.
All right. Thanks.
I think Michael was next, and then Alex after that.
Yeah. Yes. Thanks for the talk. Very interesting. So you talked about these two approaches, fuzzy and probabilistic, and then with their challenges, you had a lot of ideas, and I know in your prior work about how to solve the problems with the probabilistic approach. Do you have any ideas about how to rescue the fuzzy approach? Do you think it's just completely grim there?
Okay, so I talked a lot about this independence assumption, right? And I didn't talk much about fuzz logics here, but fuzz logics have exactly the same problem, right? So I think if you want to combine neural networks with fuzz logics, especially in this more generative AI way, the mathematics just doesn't really line up. It's still possible, but it gets really, really nasty in terms of exponential number of variables that you have. And philosophically,
you mentioned what seemed like a showstopper, just the inability, the question of how you interpret.
Yeah.
And there, maybe some of the scalability issues are common to the two approaches, but Do you have any ideas of how to deal with what you gave as really a deadly problem? Well, also the
that's true.
loss of gradient.
Yeah, so yeah, it depends a bit on how principled you want to be, I think. Like if you care more about your performance, so there's been people looking a bit more empirically, look at, okay, which of these operators best preserve your semantics. You can kind of like evaluate them in certain ways, like, and then say, well, these particular operators, they preserve these equivalences to this degree. So if you want to be very principled, I think that might not be enough, these kind of guarantees. And I think like the one set of operators that performs best in terms of like how well it is a single coherent whole, principled whole, is using this Gödel, where you basically have a min and a max. But this one, from a neural network point of view, is really quite annoying to use if you use them in a loss function, because it only has a gradient signal on a single one of your dimensions, which makes things really inefficient. So having seen all these different combinations, I kind of concluded like, to me, fuzz logic is more like high parameter tuning at this point than it really is a principled way, I think, to create neurosymbolic methods.
Thanks, Emile. And I think we have a question from Alex.
Yeah, very, very interesting. And it's certainly an area that's worth researching. I'm interested in seeing where you get to. But as a linguist and cognitive scientist, I'm aware that there's a 2,500 year legacy of people thinking about human semantics and real world semantics, and maths and statistics hasn't really been a successful way to formalize them. So I'm wondering whether you really think this is going to succeed, or whether you have use cases in mind, like self-driving cars, for instance. And I was thinking for self-driving cars, it's probably going to be much more of a pragmatic decision. You know, so Tesla might say 80% is good enough confidence for a red light, 60% is good enough confidence for a green light. And then they'd find that didn't work, and they'd increase the confidence required, and so on. So just wondering how you see this being used, or whether you had use cases in mind that it's really very good for.
Yeah, no, great question. So, so first of all, I agree with your premise. I am not claiming we should be modeling language or images or, I don't know, cognition with symbolic AI. So on the neuro-symbolic AI spectrum, I'm actually much more on the neural spectrum. I think if we can learn it, if we can model it with a neural network, we should be doing that, because many things we just cannot express purely symbolically. But that doesn't mean that that there isn't knowledge that we can use and we can exploit. So in the sciences, the response.
Decision, absolutely. Yeah.
I'm sorry.
That's a pragmatic decision. So
yeah, absolutely. Yeah, no. It's definitely not a. I think Neuro-Symbolic is actually quite pragmatic. Like you have to exploit, if you want to solve a task, you should exploit both the data and the knowledge that you have available, especially if this knowledge is very reliable. You should exploit as much as possible. That's the pragmatic philosophy behind this approach, I would say. And I think especially in many safety critical scenarios, like in medicine or in self-driving cars, having these constraints, having these requirements is just really important. But I also agree, I would not use this to model, I don't know, some kind of like linguistic structure of language. That's not something I would personally use Neuro-Symbolic for.
Emile, if I could just quickly follow up on this, unless Alex, you have a follow-up to that.
No, go ahead.
So, I mean, going back to this point, I mean, this pragmatic point. So if it is a case that you can train a neural network with sufficient data to, let's say, to get predictions right, let's say regarding the red and green constraint to 95 or 90% even. So which means that, the 10 times it gets it wrong out of 100 times, you could always have as a gatekeeper a hard constraint at the end of the output to reject if something, so this would be a non-differentiable approach, right? The differentiability is completely in the neural network. So where do you see this kind of divorced modular approach sitting in the grand scheme of things in terms of research in the area? I mean, of course, as a theoretical concept, we can continue exploring the boundaries of differentiability and logic. But if our goal really is to understand the best way to integrate hard constraints in view of applications, why would we continue looking into differentiability?
Yeah, that's also a good question. So I think there's actually many problems that get a lot easier if you can differentiate them. So controlled generation is going to be a lot easier if you can differentiate, because you can move your neural network into areas where it is more safe. Especially if you don't have enough data, allowing this differentiability gives you an infinite amount of data to move your neural network into a safe terrain. Afterwards, you can do the whole cutoff thing, and you should do it, right? Because you want to have these constraints. But if your neural network currently is not aligned with this constraint, which is actually really common, then the probability that your neural network is going to output something that complies, is this going to be really hard. And we can hope like, okay, well, if we just scale these neural networks, at some point it will learn how to do it. I think I'm not too optimistic that in a very general sense this will ever be possible. Having looked at how LLMs have been scaling, I think constraining them and doing very principled generations, I think one of the few things where it's still quite brittle. And I think having these differentiable logics can allow you to at least get you to a right area, allow you to sample better, etc.
Sounds good, Emile. Thanks very much for taking time to answer our questions and give this. We put these recordings up on YouTube. Missed a part of the talk, you can always catch. And feel free to join the mailing list. I think 1 or 2 talks in November. Thanks everybody for joining, and thanks, Emile. Bye.
Thanks so much. Have a good one.